Let's now take a look at the electric potential due to a positive and negative charge pair, i.e. a dipole. So what we have here on the left is our three-dimensional graph of the potential. So what we have is a positive charge right here in the xy plane, and we have a negative charge right here in the xy plane. And the potentials caused by them, this you can see causes a positive potential. In other words, it basically creates a hill around it. And right at this point, the potential, well, it doesn't go up to that. It would have to be infinity. It approaches infinity up here for a infinitesimal point charge of some finite charge q. And down here, this goes down to negative infinity for our negative charge. If we look at this from above, like down towards this plane, here's what it looks like right here. And the first thing we want to do is draw on this thing where the potential equals 0 other than at infinity. There is a spot on here where the potential equals 0. Where is that? Let's look at this graph over here, and you may be able to tell that there's a line that's straight right here where the potential actually is 0. And it's exactly halfway between these 2 points. See if I can draw this on here. Exactly halfway between those 2 points. It's pretty close. That is another equipotential line, exactly halfway between them, where the potential is 0, and it's also 0 at infinity, but it happens to be 0 over there. You can figure that out because kq over r, if they're the same charge, plus negative kq over r is 0 when the r's, we're exactly equidistant between these two charges. So as you can see this, you can see that it's like our positive charge is creating a hill right here. So a positive test charge would roll down the hill, but our negative charge is creating a hole. Our positive test charge would fall into the hole. So you can see the field right here is very, very steep. That's like the steepness of the hill. Notice that where the potential is 0, the field does not have to be 0. Here's our potential of 0 line right there, that red line. That's where the field is actually the very much strongest, right halfway between these two guys. As opposed to out here, I mean, it actually is stronger right there, but between them, the field is very strong. At this point right here, these lines are much closer together than they are out here. So just the potential being 0 does not mean that the field is 0. Just like on a hill, this line right there would be just like at sea level. That line is just like a line at sea level, but it's still on a steep part of the hill. So yes, you can have a potential of 0 without the field being 0. Similarly, you can have a field of 0 without the potential equaling 0. Where on this diagram do you see just that? Specifically the field being 0 with the electric potential not being 0. Just like a flat-topped hill, right here the field is 0, the steepness is 0, while it's actually high up at a high potential. In other words, inside a conductor, if it took a lot of work to get it to the conductor, then it could be a high potential even if the field inside is 0.